Hi everyone, I'm Yash, and we're a group of researchers from Tufts University here to present our work on automatic curriculum transfer from simple to complex environments. Curriculum learning is a tool in reinforcement learning that optimizes the order in which an agent gains experience. The crux of curriculum learning is to learn simpler tasks earlier while transferring knowledge to complex tasks. A classic example of curriculum learning is the game of quick chess. With each task, the number of pieces on the board increases, and so does the complexity. The components of curriculum learning are task generation that discusses how to generate these simpler tasks. Next comes task sequencing, and once I have these simpler tasks, how do I sequence them? And finally, transfer learning, which discusses how do I transfer knowledge within these tasks. There are multiple paradigms of transfer learning. We can transfer the value functions, we can transfer the policies, there's reward shaping, and so on. In order to learn a policy for a complex task in a realistic scenario, which we call the high fidelity environment as shown on the image on the left, we propose curriculum schema transfer. Firstly, we map the high fidelity target task to generate a target task in the low fidelity setting. Next, we optimize the curriculum in this low fidelity setting. And once we have the curriculum in this low fidelity, we map it back to generate a curriculum in the high fidelity. Finally, we learn the target task of the high fidelity through this mapped curriculum. A low fidelity is basically a simplified version of the high fidelity setting where the dynamics are easier to model. An overview of our process. Firstly, we map the complex high fidelity task to generate a low fidelity task as shown in the image on the bottom. Next, we optimize the curriculum in this low fidelity setting. The image below shows an example of how the optimized curriculum in the low fidelity setting looks like. Finally, we map for each source task in the curriculum in the low fidelity. We map the curriculum task parameters back to generate source tasks in the high fidelity setting. These high fidelity tasks are learned iteratively. Finally, we perform a sim to real transfer on the physical robot. We test our approach on a Minecraft-like game where an agent has to craft one stone axe. In order to craft a stone axe, it needs to collect 2 pieces of wood and 1 piece of stone. A piece of wood is obtained by breaking a tree. Similarly, a piece of stone is obtained by breaking a rock. The break action is successful only if the agent is facing the item. And similarly, the craft action is successful only if the agent is facing the crafting table. The video on the right shows how the transition dynamics of the environment. In this environment, the agent has access to 5 actions. One is move forward. The set of navigation actions include moving forward, turning clockwise, and turning counterclockwise. These actions have different dynamics in the high fidelity setting and the low fidelity setting to account for the differences in the environment. The final 2 actions are break and craft, which have similar dynamics in both the environments. The agent's observations are LiDAR-like representation along with the one-hot encoder of the inventory. For the LiDAR-like representation, the agent emits beams at incremental angles to find the closest object in the direction of the beam. The set of parametric variables include the width and height of navigable area, the number of trees, rocks, and crafting table in the environment, the number of woods and stones in the inventory, as well as the goal of the task. A source task of a curriculum is obtained by changing these parametric variables within the range given by the environment. Going over our approach once again. Firstly, we map the high fidelity target task to generate a low fidelity target task. Then we optimize the curriculum in this low fidelity. And once we have a curriculum, we map the curriculum parameters, the schema of the curriculum back to generate a curriculum in the high fidelity, and followed by learning the target task through this curriculum, and finally a sim to real transfer. This is an example of how the automated curriculum in the low fidelity looks like. The agent sequentially learns complex tasks. The state space increases and the task becomes complex, and the agent transfers the policy that it has learned in the previous task to the next task of the curriculum. The task parameters are mapped through an affine transformation between the low fidelity and the high fidelity environment. The locations of the objects are not preserved, and every time a new episode starts, the objects are randomly spawned within the boundary of the environment. Now we discuss how do we optimize the curriculum in this low fidelity environment. To optimize the curriculum, we use the beam search algorithm. We start from an empty sequence of source task parameters and assign random parameters to obtain the Markov decision process for the first source task. We learn this source task using the policy gradient approach to attain a converged policy for this first source task and repeat this procedure n times, where n is the length of the beam in the beam search algorithm. Once we have n source tasks, we find W most promising solutions given by the fewest ones to reach the stopping criteria, where W is the width of the beam. For each task in W, we initialize second source task n number of times, where n is the length of the beam, and find W most promising solutions. Here, for initializing the second source task, the learned policy of the first source task is used as the initial policy of the second source task. We repeat this until we reach the length of the curriculum, where the final task of the curriculum is the target task in the low fidelity setting. The image below shows how an automated curriculum in the low fidelity looks like. Then, once we have an optimized curriculum in the low fidelity setting, we map each source task of the curriculum to obtain a curriculum in the high fidelity. And then we learn the source tasks iteratively, finally culminating in the high fidelity target task while transferring the policy. Moving on to results, we intend to find, can the automated curriculum transfer yield sample efficient learning? Here we compare the success rate with the number of interactions different curriculum transfer approaches take. The curriculum transfer approach that I just discussed earlier, as shown in red, performs significantly better as compared to learning from scratch, which is shown in yellow, and performs equivalent to how a handcrafted curriculum from a human expert would look like. Comparing it with other baseline approaches from the literature, we see that our curriculum transfer approach, shown in red, outperforms other baseline approaches in the number of interactions taken to reach the convergence criteria. All approaches that utilize a curriculum have an offset on the x-axis to account for the sunk cost of interactions while learning the source tasks of the curriculum. Next, we make the environment too difficult to learn from scratch. In order to do this, we add a new element called fire, and the agent dies as soon as it comes in contact with fire. Our automated curriculum transfer approach, shown in red, performs significantly better as compared to learning from scratch, which does not even converge to a successful policy in the given number of interactions, and our approach performs significantly closer to how a handcrafted curriculum looks like. The automated curriculum transfer approach also outperforms other baseline approaches. Next, we intend to check, is this approach independent of the RL algorithm used to generate the curriculum? To check this, we change the reinforcement learning algorithm that was used to optimize the curriculum in the low fidelity setting, different from the one that was used to learn the high fidelity target task. And we see that irrespective of the reinforcement learning algorithm used to optimize the curriculum, the automated curriculum transfer approach works in all the cases. Finally, in some partially observable environments, it might not be possible to obtain accurate mappings from the low fidelity to the high fidelity task. For that, we intend to check, can imperfect or noisy mappings would yield successful conversions. In order to check that, we incorporate multivariate noise over the range of parametric variables. And we see that in the case of high fidelity tasks without the element of fire, the automated curriculum transfer with noisy mappings performs equivalent to the automated curriculum transfer with exact mappings while outperforming all the baselines in the literature. And in the case of high fidelity with fire, we do observe that the automated curriculum transfer with noisy mappings takes a little longer to converge in the number of interactions taken, but it still performs the other baseline approaches. The video on the left shows how the target task in the high fidelity environment on a physics-based simulator looks like. The agent needs to break 2 trees and 1 rocks to collect them in the inventory and then approach a crafting table to craft a stone axe. We perform a sim-to-real policy transfer on a physical robot where we have a turtle bot that is interacting with the fiducials on the ground, and only once it interacts with them and registers them with its inventory, only then it can move forward in the episode. In conclusion, We propose curriculum schema transfer approach called ACuTE. ACuTE optimizes the curriculum in the low fidelity environment. ACuTE maps the curriculum from the low fidelity environment is mapped back to get an optimized curriculum in the high fidelity environment. ACuTE yields sample efficient learning, is scalable to environments that are too difficult to learn from scratch. ACuTE is independent of the reinforcement learning algorithm that is used to generate the curriculum in low fidelity. It works even with noisy mappings. And finally, we observe that ACuTE is computationally inexpensive as compared to other approaches that work on generating a curriculum because of the low cost of interactions in the low fidelity environment. As a future work, we investigated, is there a unified framework that we can use to generate a low fidelity environment along with the mapping for any given high fidelity setting? We observed that utilizing an object-oriented Markov decision process representation to characterize the environment helps us in generating low fidelity tasks. The image on the left shows a turtlebot navigation domain, and the image on the right is a robotic manipulator performing the pick and place task. And we see that this object-oriented MDP representation helps us in generating the low fidelity as well as the mapping function and performs better than learning from scratch. Thank you.